Okay guys, the warm-up question for today is referring back to the motion maps that you did yesterday. In fact, you've seen this picture before. It was in the reading and it was in one of the questions in yesterday's homework assignment or classwork if you got it done in class. And it says to use the image to answer the questions, and you have two questions. The first one says examine the picture above, which car is moving faster, and then how do you know? So again, you saw this yesterday. Which one was moving faster, A or B? B. So B is moving faster because when we look at a motion map, each of those vectors, each of those arrows represents 1 second of motion. Okay, so you can look at this two different ways. The two vehicles basically move the same total distance forward. So they have the same displacement, but this car only takes 3 seconds, whereas this car takes 4 seconds. You could look at it that way. Obviously, if you travel that same distance in less time, you have to be moving faster. Or you could just look at the length of the arrows, because those arrows, because they each represent 1 second, if you go a greater distance in the same amount of time, then of course you're moving faster. Okay, so car B is moving at a faster rate of speed, and again on a motion map we can tell that by just looking at the length of the arrows, because that shows how far they're moving each second. Questions about the warm-up? Anybody have any questions? Okay. All right, so motion maps are one type of representation that we will use. They're probably the least common one though, because they're probably the hardest to read if you have a lot of data, since obviously you're going to have like 20 arrows if you have 20 seconds of data. So we use other things to represent our distance and displacement as well. And so we're going to look at some graphs and some other stuff today in our notes before we get into the assignment toward the end of the period, 103.2 distance and displacement problem set. All right, so again, if we have a motion map, it's probably not the most useful tool for us. So we're going to take information from this particular motion map and we're going to put it into a data table. And then we're going to answer a couple of questions about it, which you can look at either the map or the table to figure out. Again, each of these seconds represents, each of these arrows represents a second. So I know that the initial starting point of the car at a time of 0 seconds was at a position of 0, because that's where it starts. And that after the first second, the car is right here, halfway between 5 and 10, which means after a second, it has traveled a distance of 7.5 meters. And then it goes from 7.5 to 15 in the next second, which means it travels 7.5 meters more, but now it's at 15. And then it's at, again, halfway here, 22.5, and then it's at 30. Okay, so again, that's the information I can see from that motion map, and it may be more useful to look at it in a data table form, or maybe you're very visual and you like the motion map. But examining either of these two things, we have two questions here. How far does the car travel from 0 seconds to 1 second, and how does the distance the car travels from 3 seconds to 4 seconds compare? Okay, well, this first one's really easy. From 0 to 1 second, it obviously travels 7.5 meters. I can see that in my table. I can also just read the end of the first arrow. The second question is asking about basically the length of the arrows. Okay, how does the distance it travels from 3 to 4 seconds compare? So it's asking how does the distance traveled here from 0 to 1 compare to the distance traveled here from 3 to 4? And those vectors are exactly the same length. Every second that this car is in motion, it is moving 7.5 meters more. In fact, if you look, that's the pattern here, 7.5, 15, 22.5, 30. You're just adding 7.5 every time. So the distance traveled in each interval is the same, and I can tell that probably a little easier actually by looking at the motion map, because the arrows are the same length, and that's easier to see than trying to find these differences. If this was an easier number pattern, like 10, 20, 30, 40, it might be easier to look at in a table. All right, so again, they're traveling the same distance in each of those time intervals, and it's 7.5 meters, regardless of whether we look at the first interval or the last one. Okay, so another way to represent motion is with an XT graph. Okay, an XT graph plots time, usually in seconds, on the x-axis, and position, usually in meters, on the y-axis. XT stands for position time graph. The variable x we use for positions, the variable t we use for time. So you can write it out as position time graph or shorten it to xt graph. But you're going to be plotting in an xt graph. Your time goes on your x-axis and your position on the y. The graph will reveal the position of whatever object at various times in its motion and can show when no motion occurs at all. Same as a motion map, it's just a little bit easier for us to read, at least once you get the hang of it. All right, so let's take a look at another important note for XT graphs. The slope of the line on an XT graph, a position time graph, reveals useful information about the velocity of an object. In physics, when we talk about our graphs, our slope has meaning. Just like when we wrote our equations out, just like when you did the graphing and reasoning problem set last week, those slopes have meaning. When we write our equations, we don't use x and y, we use our variables, and therefore our slope, again, has meaning as well. You saw that in the assignment last week. All right, so looking at this position time graph, and this is basically what they look like. You're going to see position on your y-axis. You're going to see time on your x. Sometimes instead of the whole word, it'll just say x and t. Either way is fine. But it says, what can you tell me about this object's motion? What happens to its position after 1 second? I'd like you to take a look at it, turn and talk to your neighbor, especially if you're not sure, but if you are, tell them what you think is happening. Because I'm going to call on somebody in a minute, and I want you guys to have an answer ready for me for what you think is happening. So you have 25 seconds to discuss. Okay, so what can you tell me about the motion of this object, Tanisha?
It's not moving.
It's not moving. Perfect. Okay, if you look at this graph, what happens to its position after 1 second? Nothing. Its position is at 6 meters the entire time, which means it's not going anywhere. This object, because it stays at 6 meters the entire time, it can't be moving at all. So if an object is stationary, if an object is at rest, you're going to see a horizontal line. A slope of 0 is going to tell you that you have a velocity of 0. Okay, what about this graph? Again, take a moment, look at it, think about what's happening to the motion of this object, or if it's moving or not. And again, turn and talk to your neighbor, and I'm going to ask somebody to tell me what they think is going on in 24 seconds. Sounds like y'all already got that one figured out. All right, so what did you guys say, Ainsley? Yeah, it's moving 2 meters every second. After 1 second, it's at 2. After 2 seconds, it's at 4. After 3 seconds, it's at 6. Okay, and so you can tell that this object is moving with a constant speed of 2 meters per second based on this graph. Okay, so again, if you see a straight line like this one, okay, it means that your object has a constant velocity. All right, does this object change direction and start moving backwards at any time during its motion? Do we see that on the graph? No. Okay, we do not see any change in motion. Okay, what do you think it would look like if this object were going backwards instead of forward? Yes?
It would start sloping down.
Yeah, my slope would go in the negative direction instead, because I would start moving back toward a position of 0. It looks something like this. This object is moving backwards the whole time. This green one is moving forward the whole time. I told you slope has meaning, so now you know if you have a positive slope, it means that you are moving in a positive direction. You have a positive velocity. If you have a negative slope, it means that you are moving in a negative direction. You have a negative velocity. So again, if you're taking notes, that would be a helpful thing to write down. And again, zero slope means zero velocity. You're not moving at all. Okay, so again, you can tell from these graphs information just like that. As we already determined, this object moves at a speed of 2 meters per second. If it were twice as fast, how would its displacement differ each second? So if it were twice as fast, what does that tell me about its displacement? What do you think, Annika? Sorry? What it says on the screen. If it's twice as fast, how does its displacement differ each second? Or how would your graph look different?
Slopes would be like twice as high.
Yeah, you'd have a steeper slope, a slope that's twice as high. You'd be going twice as far each second. Okay, so if your displacement's twice as much, you'd have a slope that was twice as steep. It would look like this. So instead of going 2 meters, it would go 4. And then instead of being at 4, it would be at 8. And so if you have a steeper slope, it means your object is moving faster. If you have a more shallow slope, the closer it gets to horizontal, the slower it's moving. Of course, if it is horizontal, it's not moving. So there's a lot you can tell by looking at the slope of the line on an XT graph. We've already went over each of these bullet points, but if you don't have them written down in your notes, this might be a helpful thing for you to write. The slope of 0, a horizontal line, means the object isn't moving. A positive slope means the object is moving forward. A negative slope means the object is moving backward. A steep slope means the object is moving faster. And a shallow slope means the object is moving slower. Okay, so we just went over all of those things. And you can tell just by analyzing the graph. You guys were able to do that. We hadn't even gone over it yet. But this part right here, being able to analyze graphs, is going to come back over and over and over again throughout the year, not just this unit, the entire year. Okay, and it is something that students struggle with because graphical representation can be difficult. It can be harder to look at it than just looking at a data set or a data table. But you guys have to get into the habit of analyzing, what does the slope of this line mean? Okay, what does this tell me? And it's not always a a position time graph, but we'll see it throughout the year in different types of graphs. But there is meaning to those slopes, so make sure you pay attention to them. All right, so this is back to our question that we had on our slide right after the warm-up. And it says, draw a graph showing the same motion. Well, I already know that this car is moving forward and that it's moving at a constant speed. So I know I'm going to have a straight line that is a positive slope. Okay, and I can plot those points because I already have a data table here. So my points, I have 0, 0. I have a point at 1 and 7.5, at 2 and 15, at 3 and 22.5, and at 4 and 30. And you'll notice they fall on a straight line. Real world data, probably not that perfect, but that's okay. You'll get them at least close to a straight line if you have an object that is moving at constant speed. Okay, so that is exactly what you would expect that to look like. So you should be able to go from a motion map to a position time graph or vice versa. You should be able to go from one to the other. If I give you one, I can ask you to draw the other or to match it on a multiple choice type question. You will be asked to do that later on. All right, we can also use position versus time graphs to determine an object's distance traveled or its total displacement. So on my screen right now, I have a position time graph. This one has 3 different sections of motion. It's not doing the same thing the whole time. I can tell that because its slope changes. Okay, and I have 3 different slopes up there. But I'm not even looking at that. I'm just looking for what is its displacement, what is its distance. Okay, and so if I want to determine my displacement is just like it was yesterday, your change in position. So all you have to do for displacement is find out where you started. So according to this graph, I started at a position of 0. And then find out where you ended. According to this graph, I ended at a position of 25. So if I move from 0 to 25 meters, my displacement is positive 25 meters. That would be the answer to the first question. What is my distance in this graph? Take a moment, look at it. If you're not sure, turn and ask your neighbor what they think the distance is. But see if you guys can come up with an answer, because I'm going to call on somebody in a second to tell me what the distance is in this graph. All right, what do you think, Bram? What is our distance?
I think it's 25 meters.
It is 25 meters. Did this object ever go backwards? No. Guys, remember I told you yesterday, if all you do is go forward, your distance and displacement will be the same. I'm aware this went forward and stopped, but that's obviously not going to change distance or displacement. Forward, stop, forward, they're going to be equal. Okay, so distance is also 25 meters. You'll notice I did not put the sign on it because I don't need a direction. For distance, it is a scalar quantity. All right, how to tell distance and displacement on an XT graph. We just did it. Distance is the sum total of all forward motion and all backward motion. That graph didn't have any backward motion to add, so we just added all the forward motion. Displacement is how far you end from where you started. If you end at the same position where you started, then your displacement is 0. We talked about that scenario yesterday as well, several times, about things that were walking forward and backward, or like the warm-up where it went in a box, or you go a lap on a track, whatever. But your displacement is how far you are from where you started. So we can tell both of these things from a graph. Let's look at another graph and see if we can, again, look for the distance and displacement in this graph. Okay, so here's a different position time graph. I would like you to take a moment to look at it, and you can discuss it with your neighbors so that you're ready to be called on in case I pick you. But see if you guys can agree or come to an answer for what is the displacement in this graph, and then what is the distance in this graph. So take a moment, turn and talk to your neighbor, take a look at my graph. You guys have 30 seconds to discuss.
Oh, yes. So, yeah.
All right, hopefully that was enough time. Let's see, Wyatt, what did you say for your displacement?
-40.
-40. Again, all you do for displacement, that is correct, by the way. All you do for displacement, here's where I started, here's where I ended. How far am I from where I started? And I am specifically 40 meters in the negative direction. I do need to indicate my direction, so -40. All right, what about my total, good job, Wyatt, thank you. What about my total distance? What did you say for that, Brant?
This is 180.
I honestly don't remember. Let's look. So distance, this is what you do for distance, because this time we do have forward and backward motion. So you go from 0 to 60, so there's 60. And then from 60 back to 0, if you want to stop there, sure, 120. And then from 0 to 40, so add 40 more to that. So 120 plus 40, 160. Okay, do I care that I went forward or backward? No, I'm just going to add everything together. 160 meters would be your total distance. Okay, so it's obviously quite a bit faster to find your total displacement than it is your total distance, especially if you have a complicated graph with a lot of back and forth. But you can find both of them by looking at these graphs. All right, guys, so for the remainder of the class period today, you have an assignment. Again, you can open up the same Google sheet that you were using yesterday. It has your links in it. So if you go back to Schoology and open up the 103 problem sets sheet, again, this one, it looks like this. You should already have your ID typed in there. And then you should have a link here for today that you can use, and it'll open up your Google form with your questions. You can work on this for the remainder of the class period, which you guys have like 7 minutes, something like that. But whatever you don't finish, you can finish for homework, and you probably won't end up with any if you are working on it in here. But you're welcome to discuss with a neighbor. But I mentioned this yesterday. The questions you have may not be the same questions they have. Yesterday's actually wasn't randomized, but the one today is. So just be aware of that. If you're talking through something, make sure you're reading the question, because you're not necessarily answering the same thing your neighbor is. And that should always be the case. I don't ever want you just copying somebody, but I am perfectly fine with you saying, hey, Brant, can you show me how to do this one? How did you do it? That's fine. Okay. Again, there is math involved in some of these questions, so you may want to have some paper out. It's really difficult to do math on a computer without paper. So if you need paper out, go ahead and get that. And again, if you have questions as you're working, please let me know.